Okay, this video is going to go over the graphs of the other four trig functions, the tangent, cotangent, cosecant, and secant functions. Alright, we're going to start with the graph of the tangent function. Remember, tangent is equal to sine over cosine. So what we're going to do, we already just showed the graph on the previous slides, but now we're going to show how we get that shape. We're going to show why it looks like this. We already said that it looks like this, now we're going to discuss why. If we start by plotting a table of values, or by writing down a table of values. Alright, so remember, tangent is equal to sine over cosine, so the way we get the y values is, like say for negative 3, the sine value of negative pi over 3. Remember, that's whenever you start at the x-axis and you go downward, pi over 3 units, so that's negative pi over 3. So that's this angle right here. The sine value would be negative square root of 3 over 2. And the x value, since x is still positive, that'd be positive 1/2, so that's why it's negative square root of 3, or approximately negative 1.73. For negative pi over 4, that's whenever you go pi over 4 in the negative direction. The sine value would be negative, so it would be negative square root of 2 over 2. Remember, we get these values from the unit circle, and the cosine would be positive square root of 2 over 2.
I stayed for that.
Remember, so for negative pi over 6, if you were to go pi over 6 in the negative direction, the sign would be negative, so it would be negative 1/2. And then cosine would be, cosine's still positive, so it would be positive square root of 3 over 2. So that'd be, if you do keep flip change, that'd be negative 1/2 times 2 over square root of 3, which would be negative 1 over square root of 3, multiplied by square root of 3 over square root of 3. That's how you get negative square root of 3 over 3, which is approximately negative 0.58. So if you notice, that's kind of how we get these. And whenever you go to the positive values, like positive pi over 6, it's the same value as negative, just since the sign is positive as well in the first quadrant, which is where these are. Since these angles are in the first quadrant, the sine and cosine have the same sign, which means tangent would be positive. So that's why these are positive. And since these are in the fourth quadrant, where sine is negative and cosine is positive, that's why tangent is negative. If you notice, all the y values are increasing as the x values increase. And we said there were, I think we said in a previous video, there were asymptotes at intervals of k pi over 2. With k being an odd integer. This is because tangent, we just said, was sine over cosine. And cosine is equal to 0 at intervals of k pi over 2, where k is odd, like 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. So now, let's go ahead and display the graph up there again in case you've forgotten. Alright, so here's the graph of the tangent function. We're going to look exactly why there's an asymptote here at, say, pi over 2. We're going to look see what happens to the y values as it approaches pi over 2 from the left-hand side of the asymptote. Now, to see what happens as the graph approaches pi over 2 from the left-hand side, if you plug in values that are increasingly close to pi over 2, so you start at pi over 3, you get a tangent value of square root of 3, or approximately 1.73. Plug in 1.5, the x value gets close, or the sine value gets closer to 1 because sine of pi over 2 is 1, and the cosine value decreases to roughly 0.0707 because cosine of pi over 2 is 0. So the y values consistently increase because the y values are getting closer to 1 and the x values are getting closer to 0 as you get closer to pi over 2, because again we said cosine of pi over 2 is 0. So when the y values are increasing and the x values are decreasing, that means the quotient y over x is increasing exponentially, as you can see here. Since tangent never approaches a certain value, because cosine can never be 0 in the tangent function, that's why it's undefined. And that's why there's an asymptote. And one thing I would like to point out about this graph before we go over the characteristics is you see where all the x-intercepts are located. They are located exactly halfway between each asymptote. If you remember the period, the tangent function had a period of pi. So each asymptote is at a period of pi, and halfway in between each asymptote are the intercepts. And each intercept is also located pi units apart. That's how you know that the period of tangent is pi. Now here are some properties listed for the tangent function. Alright, we already said the domain is the set of all real numbers except for values of k pi over 2, except where k is odd. That's what point 1 means. The range, since each branch goes in the positive and negative y direction infinitely, the range is just the set of all real numbers. Now the tangent is odd, and here's why tangent is an odd function. If we plug in negative x, that's the same as sine of negative x over cosine of negative x. Now we said sine is odd, so the negative can be moved to the outside, so that's negative sine of x over cosine of x we said was even, so that just turns into cosine of x. So you just end up with negative sine over cosine, which is negative tangent. So that's why tangent is odd. We already said tangent has a period of pi, and the x-intercepts are at multiples of pi, multiples of k pi, where k is an integer. And you see all the values that are not in the domain? That's where the vertical asymptotes are located. And the x-intercepts are located halfway between each asymptote. Alright, here's an example graph, y equals 2 tangent of x minus 1, and use the graph to determine the domain and range of the function. So let's start with the graph of just tangent of x. Alright, so now this graph of the tangent function, we know the amplitude is 2, so it's just going to go up at a higher rate. So this branch would go something like that. This branch would go up about twice as fast. The asymptotes would still be located at the same place. The x-intercept would still be at the same place. But now each of these branches, like the intercept would be shifted down 1 unit. So that'd be like this. So it'd actually be the blue graph down here. Because the minus 1 tells you that the vertical shift is down 1 unit. So pretty much you stretch each branch by a factor of 2, then shift it down 1 unit. In the domain, we didn't do any sort of change to the period, so the domain looks like it'd still be the set of all x values such that x cannot be at intervals of k pi over 2, with k being odd. And the range looks like it'd still be all real numbers. Alright, so let's try graphing this one. Alright, y equals 3 tangent of 2x. Alright, the amplitude is 3, and the period, we said the period of tangent is normally pi, but we have to divide by the number in front, so the period's now pi over 2, meaning it's cut in half. So let's start with the graph of the original function to use it as a reference. So since the amplitude is 3, and the period's been cut in half, we'll start at where x equals 0. If you multiply x equals 0 by 1/2, since the period was cut in half, it'd still be at 0, so this branch would still cross the x-axis at the origin. But since it's an amplitude of 3 now, you'd stretch it by a factor of 3, and that branch would look something like that. Now this asymptote right here is located at, I believe, pi over 2. Multiply that by 1/2 because the period's been cut in half, so now that'd be at pi over 4. So here would be, let me put the asymptote in a different color. It'd be right here at pi over 4. This place, range here at pi, multiply that by 1/2, that'd be at pi over 2. This asymptote here at negative 1/2, that'd be at negative 1/4. So that asymptote would be right here. So if you notice, it's just squeezed a lot more together. That's what that graph would look like. So now let's figure out the domain. The domain would be the set of all x values such that, if you notice, the asymptotes would now be at intervals of, right, this would be this asymptote at 3 pi over 2. Since the period was cut in half, it'd be at 3 pi over 4 now. Like right there. So it'd be a set of all x values, it looks like, such that x cannot be at k pi over 4 now, with k being odd. And the range still looks like it'd be the set of all real numbers. Now we'll go over the graph of the cotangent function. Now if you remember, the graph looks something like this. Looks similar to the tangent function, except the branches go in the opposite direction. Something like that. And the reason why is because, remember, with cotangent, we have cosine on top and sine on the bottom. So that means, for one, the location of the asymptotes change. Instead of it being at intervals of k pi over 2, where k is odd, x can now no longer be intervals of k pi, where k is an integer, so like pi, 2 pi, 3 pi, 0 pi, or 0. Like that could be at pi, then at 2 pi. So since the reason it can't be there is because sine of theta is 0 at values of k pi. If you go look on the unit circle, at intervals of k pi is where it crosses the x-axis, so the y value or the sine is 0. Here's a nice, neat graph of what the cotangent would look like. There's the graph. I just drew a rough sketch of it on the previous slide. And here's why they're going downward, if you want to look at the table of values I'm about to put up here. Alright, so, if you notice, at pi over 6 cotangent, which is just cosine over sine, is just pi over 3, or square root of 3. At pi over 4, cotangent is 1. Remember, cotangent is just cosine of theta over sine of theta. So like at pi over 6, cosine of pi over 6 would be 1/2. No, it'd actually be square root of 3 over 2. I had to think about that for a minute. Cosine of pi over 6 would be square root of 3 over 2. And the sine of pi over 6 would be 1/2. So if you do keep flip change, square root of 3 over 2 times 2 over 1. The 2's cancel out, so you're just left with square root of 3. That's how you get the y value. So pi over 6. So at pi over 6, the cotangent is just equal to the square root of 3. At pi over 4, it's equal to 1 because cosine of pi over 4 is square root of 2 over 2. Likewise, the sine of pi over 4 is square root of 2 over 2. So that's how you get 1 for the cotangent of pi over 4. And that's the idea between each of these y values. You divide the cosine value on the unit circle by the sine value. And that's how you get the corresponding y value. And the characteristics of the cotangent are pretty much identical to the characteristics of the tangent. Just keep in mind the domain is different. The domain for this is the set of all x values, such that x cannot be an interval, be in multiple of k pi. It cannot be like 0 pi or 0. It can't be pi or 2 pi or 3 pi, because that would make sine equal to 0, which would make the cotangent function undefined. Now let's go over the graph of the cosecant and secant functions. We obtain these graphs by applying our reciprocal identities that we learned earlier. We learned that cosecant we get by flipping the sine function, and the secant we get by flipping the cosine function. Alright, notice this black graph is the sine function. So if you just take these, I guess call them the little bumps in the sine function, instead of the range being between -1 and +1, if we're doing 1 over the sine of x, instead of it being contained between -1 and +1, the range would be that the range of the reciprocal would mean that instead of it being contained in between these two y values, it's contained outside of the y values. So that's how you know to draw the branches in this manner. And you know there are asymptotes here because secant is, or cosecant rather. Have I been saying secant? Cosecant, because this is the graph, this blue graph is the graph of the secant function. It's did it again, it's supposed to be cosecant. It is the cosecant function, the blue graph is the graph of the cosecant. Alright. We know to draw the graph of the cosecant outward because whenever you flip it, instead of it being contained in between these y values, it's contained outside. And just to note, the domain, since we have asymptotes at intervals of pi, the domain would be the set of all x values such that x cannot equal k pi, with k being an integer. Likewise for the secant function, which is just 1 over the cosine. Here's the graph of it. For the same reasons, we know to draw it outward because if our original function cosine is contained in between -1 and +1, then whenever we flip it, the range would be flipped as well. So instead of being contained on the inside here, it's contained outside this range. So that's how you know to draw it outside -1 and +1 respectively. Alright, and the domain for the secant, just set of all x's such that x cannot be at intervals of k pi over 2, where k is odd, because that would make cosine equal to 0. And the range would be the set of all y values such that -1 is less than or equal to, actually -1 would be greater than or equal to y, because it wants all the, because we have all the y values, say here, that are less than -1, so -1 would be greater than or equal to y, and like on the upward facing branches, like here, those would be all the values that are greater than or equal to +1. So that's the range for the secant. Likewise for the cosecant as well. Alright, so here's the last example of this video. Graph 2 cosecant of x minus 1. Let's determine the domain and range of the function from the graph. Alright, so now if we graph y equals cosecant of x minus 1. Let's start with just the graph of cosecant, which would be your blue graph. Your amplitude would be 2, and this -1 means your vertical shift would be down 1 unit. So each of these branches now would shift down 1 unit. Now it shift down, and the branches would just be more narrow because the amplitude is 2. It's not shifted to the left or to the right. So the period didn't change, so the domain would still be the set of all x values such that x cannot be k pi, where k is an integer. And the range is still the same. It still be the set of all y values such that, actually it wouldn't be the same because we did shift it down vertically. So it'd be all the y values less than or equal to -2, so -2 greater than or equal to y. It'd be all the y values greater than 0, greater than or equal to 0.